Class on Lorentz force, we consider that we discuss that whenever a charged particle q moving with velocity v is subjected to a magnetic field b, then the force acts on it is this. If we convert this into the force that acts on a current carrying conductor, so if we have a current element IDR, then the force that acts on this current element is dF. For 2D conductor, this becomes Js ds cross b, and for 3D conductor it is J dV cross b. This is the force that acts on a current carrying conductor. And if you want to find out the total force, one has to integrate it over the geometry of the conductor. Special interest was paid on closed current loop, closed elementary current loop. Whenever an elementary current loop delta C is a closed current loop which encloses an area delta S, since it is an elementary loop, the area is small, so it can be considered to be a vector, and we call the A vector area this. Then we found that the force that acts on this if we call it delta F, the force acting on an elementary loop is this, and this is given by delta M where delta M is defined as I times delta S, which is I times integration over delta S ds. And this force is 0 when the contour is placed in a uniform field, and if we place it the elementary contour in a uniform field, then the torque that acts on it is given by delta M cross B for B is equal to uniform. For non-uniform B, other terms appears. This is the thing that we have discussed in the earlier class. In this discussion, we assume that somehow the magnetic field has been created, and either the charge or the conductor has been placed in the existing magnetic field. Today we will discuss what happens what is the force that acts between two current carrying conductors, that is the force or interaction force between two current carrying conductors. So what we have a conductor tau 1 which carries the current I1, and we have another conductor tau 2 which carries the current I2. Our objective is to find out what is the force that acts on an current element I2 dr2 on tau 2 due to a current element I1 dr1 on tau 1. So we consider a current element. This is I1 dr1, where r1 is the position vector, and this we have r2. This is I2 dr2, and this is the relative separation. R is equal to R2 minus R1. So our first thing is what is the field at this? We call this point P2 and this point is P1. So field dB21 is equal to field at P2 due to I1 dR1 at P1. So what is the field over here due to this current element? As per Biot-Savart law, this is mu 0 I1 upon 4 pi dR1 cross R by R cube. And similarly, B21 is obtained by replacing I1 by I2, R1 by R2 and capital R, vector R by minus R, because in that case we will have the position vector from here to there. Similarly, so dB12 is equal to mu 0 I1 upon 4 pi dR2 cross minus R, and this is R cube, so minus sign is here. Now we want to find out what is the field force that acts on there, on I2 dR2 due to this. So we call it D2F21. This is equal to force on I2 dR2 at P2 due to I1 dR1 at P1. So this is equal to I2 dR2 cross the field that is produced by this over there. So the nomenclature that we have used, that it is on and second suffix is due to. So if we write this will be mu 0 I1 I2 upon 4 pi R cube dR2 cross dR1 cross R. And similarly, the first thing, there's this double differentiation. A double differential is because it is involves two differentials or two elementary quantities. Similarly, if we want to find out the force on 1 due to 2, this will be I1 dR1 this is this effect. We can break it up into two components. This is equal to mu 0 I1 I2 by 4 pi R cube. This is this part, and this part is dR1 Similarly, this is equal to minus mu 0 I1 I2 4 pi R cube you see that the force, these two parts are equal and opposite, but these two are not. This is the force on the conductor 2 due to 1, which has a component along this. So there will be a component here. The field will have two components. one is along dr1 and other one is along minus r. And in this case, the field will have two components. One is along dr2 and other one is along minus r. Sorry, plus r, minus plus r. So these two parts are equal. So these two parts are equal and opposite, but these two parts are in general different. So if we talk about Newton's third law, if you see that the Newton's third law is not even valid in its weak form. If we consider this is the action force, and if we consider this is the reaction force, then they are not even equal. Newton's third law has two forms. When two bodies interacts with each other, if we call this action, if we call it action, and this is called reaction. When the action and reaction are equal and opposite and acts along the line joining them, it is called a strong form of Newton's third law. Another situation may arise when action and reaction are equal and opposite, but they do not act along the same line. This is known as the weak form of Newton's third law. Here we see that the Newton's law is not even valid in its weak form. So if we re-examine the case, what is the reason for it? We see that we have considered a conductor which carries a current. A conductor may carry a current when it forms a closed loop. So a conductor carries a current and there should have a source of EMF. And when the conductor forms a closed loop, then only the current flows. Another situation we have that the conductor is infinite conductor, so that we consider a conductor of very long length and it forms a closed path of a circle of infinite radius. So the two situation is either it should be a closed, both of them are closed conductor, or both of them must be straight conductors. We shall consider these two. Before going to that, the total force on conductor 2 due to 1. This is force on tau 2 due to tau 1. This is obtained by integrating this expression, that is integration over tau 1 integration over tau 2 d2f21. Similarly, we can get expression for df on 1 2. This is order of integration is immaterial. 1 2. If we have for closed conductor, then for closed conductor, closed wires, then tau 1 will be replaced by C1. So this is C1, C2, D2F21, and so we are going to consider this expression first. So what we shall first do, we shall write these two forms first, and D2F21 is equal to mu 0 I1 I2 upon 4 pi r cube, then this part. So if we want to find out the total force, then we must integrate over both the contours, and in which case you find that these two are equal and opposite, and we do not bother for this term. Rather, we want to examine what happens to these two terms. So let me consider what happens to the term which appears to be in problem. So if we consider this term together with r cube, we have dr1 times r dot dr2 by 1 by r cube. This part we consider it like this. You note that as per our choice, r is equal to r2 minus r1. That is I cap x2 minus x1 j cap y2 minus y1 plus k cap j2 minus z1, and r is its magnitude. So what is the divergence 2 of 1 by r? By divergence 2 we mean I cap del del x2 plus j cap del del y2 plus k cap del del z2 operating on 1 by r. If we consider the first term only means del del x2 operating on 1 by r. This is equal to minus 1 by r square del r del x2. If we differentiate this, this is r square. So if we differentiate it, this gives you twice r del x2 is equal to twice x2 minus x1. So this is equal to minus x2 by x r cube. If we consider such terms, it readily gives you minus r by r cube. If the differentiation were note that as per our choice, it will be plus r by r cube. So what we get as this term is equal to minus dr1. This part we write as this is of the form that grad phi dot dr is equal to d phi. So this part is actually equal to minus dr1 d2 1 by r. Because there is dr2, so we perform the Navla operation with respect to same base, so that we can write it like this. If we integrate this one, as this is a perfect differential, so when we integrate over C2, this is equal to 0. Similarly, this term can be written as dr2 d1 1 by r, and integration over c1 d1 1 by r is 0. So we see that whenever we integrate this expression over to closed conductor, this part vanishes due to this term when one integrates it over conductor 2, and this term goes, sorry, I have made a mistake, this should be 1, and this term goes when one integrates over C1. That is what we get is we rewrite this to d2f21 is equal to mu 0 I1 I2 upon 4 pi, and then this part dr1 d2 1 upon r with a minus sign, and d2f12, this term the minus sign is being adjusted, this minus sign is makes it plus. From here we get this part goes on C2 integration, so the result is let me write the SI factors, minus mu 0 I1 I2 by 4 pi, and then we will have C1 C2 and for F12 we get this is plus So we see that whenever we apply the Amperes Force Law between two closed conductors, Newton's third law is valid in its strong form. For each pair, the force is along the r direction. Now we come to the another possibility that was left, that is force between two straight current carrying conductors. We consider two conductors, straight conductor carries current which are parallel to z-axis and carries current along positive z-axis, and our aim is to find out the force that acts on the conductor. So this is our coordinate system: x, y, z. This is for conductor 1. This carries a current I1, and this is another conductor carries a current I2. This is both are carrying currents on positive direction, and along z-axis this separation is a and this separation is b, so the separation between these two is b minus a. So this is a y is equal to a line, this is y is equal to a line, and this is y is equal to b line, and we assume that the wires lie in the x is equal to 0 plane. Lie in x is equal to 0 plane. So the position vector on conductor 1 will have j cap a plus k cap z1, which gives you dr1 is equal to k cap dz1, and for conductor 2 this is r2 is equal to j cap b plus z2, which gives you and r is the position vector. So we consider this much is z1 and this is dz1, this is z2 and this is dz2. So the r is this one. This is capital R. This is R2. This much is R1. So this is equal to j cap b minus a plus k cap z2 minus z1. Now the force are force on 2 due to 1, on due to, the notation that we have used. This is equal to I2 dr2 cross dB to 1. If we write it explicitly, this becomes for this I1, this is k cap dz1 cross r. For r we write this one. So this should be third bracket, and now the thing is that I1 has taken twice, so this is mu 0 I1 I2 by 4 pi r cube, then k cap dz to k cap dz2 cross this part. K cross k is 0 and this part will survive. K cross j is minus I, so this is minus I cap dz1, and this is b minus a. So if we write it, minus mu 0 I1 I2 upon 4 pi r cube dz1 dz2, so this is b minus a dz1 dz2, and the vector direction is this, k cross I is plus j, so it is along, since this is positive, and this force is on the negative y-axis, that is the force that acts on the conductor 2 due to conductor 1 is along this direction. If we carry out the calculation of d2f12, it will come out to be j cap mu 0 I1 I2 I1 I2 by 4 pi r cube b minus a dz1 dz2. So the force is in this direction. So we see that the force due to two current elements for a straight conducting wire, they are equal and opposite but do not act along the line joining them. They are not acting along plus minus r, but they are shifted. So the Newton's third law for straight conductor is found to be valid in its weak form. If the current flow, here we see that the force is such that it tries to bring the conductor closer to each other. If the current flows in opposite direction in one wire, then say current flows along conductor straight line, 1 in the upward direction and 2 in the downward direction, then I2 will be negative. If I2 becomes negative, then the force on conductor 2 will be reversed and it will be in this direction, and so is for this. So there will be a repulsion when the two conductors, straight conductor carries the current in opposite sense. Due to the Lorentz force, the conductor are pushed away. This is something different from what we have in Coulomb's law. In Coulomb's law, we found that whenever the charges are similar, there is a repulsion, and when the charges are dissimilar, there is attraction. Here for straight conductor, we find that when the current flows in the same direction, the conductor tries to come closer to each other, and when current flows in the opposite direction, the conductors are pushed away from each other. Sometimes this expression is considered as the basic equation of magnetostatics, and it is known as Amperes Force Law. This is the law which governs the force that acts between two current elements. In few books, magnetostatics is started with this expression, and then one comes to the expression for V by introducing Ball-Savart law. Another thing is that this expression can be used to define B. The definition of B sometimes uses this expression.